Hello, everyone. Welcome to today's Field Advisor webinar. Thank you for being here and taking time out of your day. I'm really excited to get started. So first of all, my name's Kelsey Litchfield. I'm the Agronomy Outreach Manager and Editor of Field Advisor here at Illinois Soybean Association. Today, I'm also being assisted by Lauren Hill, who's our Agronomy Outreach Specialist as well here at Illinois Soybean. So first, real quick, if you aren't familiar with Field Advisor, we are a program funded by the Illinois Soybean Checkoff Program, providing the latest agronomic information, on-farm research from local experts like we have here today to help Illinois soybean producers improve yield and profitability. Field Advisor is an independent, unbiased media platform with blogs, video, a podcast, webinars, and events for those interested in agronomy and crop production. So before we begin, some quick housekeeping items. This webinar is being recorded and will be available after the live session. It will be emailed out along with a survey and on Field Advisor's YouTube channel. And one CEU credit in crop management is available. If you are watching this webinar live, a QR code will be available at the end of this presentation. And then if you're watching the recording, we recommend self-reporting for the CEU credit. If you're unsure how to do that, just please email fieldadvisor@illsoy.org for assistance. And of course, questions are welcomed. Our presenters will start their own presentations, and then we will have a Q&A section. If you have questions throughout the webinar, feel free to put it in the chat box. We've also received questions in advance, so thank you to those that submitted those. And I know they will answer those throughout their presentation as well. So I'll go ahead and quickly introduce our speakers today. We have Dr. Connor Sible. He is a research assistant professor in the Department of Crop Sciences at the University of Illinois, where he also earned his master's and PhD degrees. His research focuses on corn and soybean production systems with an emphasis on optimizing the interaction between agronomic products and management practices to improve grain yield and nutrient use efficiency. His work includes evaluating biological and biostimulant products, fertilizer strategies, and crop residue management to enhance soil nutrient availability. He regularly presents his research at field days, extension meetings, national trade shows, and international conferences. So welcome, Connor. We're excited to have you here. Ava Isaacs is a master's student in the Crop Physiology Lab at the University of Illinois. Her research focuses on agricultural biologicals and nutrient use efficiency, with particular emphasis on how biological products vary in efficacy across environments and regions, as well as how their performance changes under different management systems and across hybrid or variety genetics. Her work centers on improving fertilizer use efficiency and evaluating the impacts of biologicals on soil and plant health. The goal of her research is to help farmers better understand this emerging product market, as we all want to, as they make input decisions to maximize yield and field productivity. So welcome, Ava. We're excited to have you here as well. And now we'll go ahead and turn it over to Connor to start us off. Thank you.
Got our screen? Looks good.
Yep, looks good. Thank you.
Awesome. Well, thank you so much, everybody, for joining us today. Really excited to have the opportunity to talk to you about residue. We got the question that we posed for you, right? Trash or treasure? And how do we then maximize the value of the residue? Kelsey did a great job introducing myself and Ava. Really excited to have Ava here today. We are two members of the Crop Physiology program. So before we get into the nitty-gritty of the residues and how we're going to manage it, we do have to give a shout out here to the team that gets it done. It does take a small army to do the crop physiology research program. This was our team in 2025. I have worked now going on, this will be my 10th growing season working with Dr. Fred Bilo in the Crop Physiology Lab. Time goes fast. Hard to believe been here that long. Worked as a graduate student, a postdoc, and then joining the faculty just a little over a year and a half ago. Been a really exciting time and working with some great individuals. So this is just the 2025 team. A lot of people have come and gone. Takes two principal research specialists, Julianne Seebauer and Jared Fender. We have a postdoc, Dr. Marley Favoretto, and all of our graduate students. And if you look pretty closely, you notice one of our master's students here, Ava Isaacs. currently in the 2025 season and going into 2026 spring as a master's student. I'm a real glutton for punishment, aren't you, Ava? Really likes the research, what she's been doing. And so happy to say in 2026, as we update that, Ava is going to be transitioning to her PhD. And you could probably guess what topic that might be. But at this point, I'm happy to introduce to you Ava Isaacs, and she'll start our discussion today on residue management. So take it away, Ava.
Thank you for the introduction. Yeah, my name's Ava Isaacs. So I'm really excited to start my PhD and really, get into new avenues of research here. But throughout my master's degree, I worked with biologicals mainly in soybean. And so, there's a big question surrounding all of that, and it leads back to crop nutrition, right? So how do we traditionally think about crop nutrition? There's usually two different sectors. So there's the soil and there's also fertilizer. Those are kind of interchangeable. So, when your soil is, if your soil is not meeting your crop needs, then you're adding fertilizer. It's in this big rotation. And what kind of drives these cycles? That's our plant growth, as well as, soil sciences. So those microbes in the soil. And what do we call this big, cycling? Well, we usually refer to it as agronomy. And so there's actually been this new shift. There's a lot of buzzwords going around: regenerative agriculture, sustainable agriculture. So there's a big consumer shift towards those. And in that, we've kind of seen we're kind of going away from our chemical-based systems more towards biological-based systems. And so with that, residue is a really big topic in this. And so where does our residue really come from? There's usually three main avenues. So there's, cover crops, there's cereal rye, double crops, so wheat residue, as well as higher yields. And sometimes farmers come to us and they're like, okay, well, I don't do cover crops and I don't do double crops, so why should I be really concerned about residue? And I usually say, okay, well, if you don't do either of those, you've had higher yields, right? We've had, advances in genetics and advances in management, so we are seeing higher yields. And no matter where you farm, you're definitely dealing with higher yields. And with higher yields, you usually have higher residue, right? So this is some work that Dr. Ross Bender did a couple years ago. So it's residue by grain yield level. So in this, we kind of see as grain yield goes up, so does our stover biomass. And kind of put a number with this, for every bushel of corn that you increase, it's 44 more pounds of residue. So if you're increasing, your yield by 20 bushels an acre, that's 880 pounds of residue that you're adding back onto the field on top of already what's there. So for visual learners like me, I have to have a number to kind of put with it. So I can give you that graph. You're like, okay, but I actually want to see what's going on in the field, right? So for our grain yield, if you're around 180 bushels an acre, you're looking at around 4 tons per acre of residue in your field. And then, as we've gone through the years, everybody's pushing for a higher yield, getting into the 300s. You have, over 6.5 tons an acre of residue, up into those record-setting yields of 616. That's 13.5 tons of residue an acre. So that's a lot, right? And so this kind of gets us into this aspect of, okay, is that much residue a good thing or a bad thing? So is residue trash or is it treasure? You're kind of thinking, okay, residue can't be a bad thing, but in certain situations maybe it can. That's kind of getting to the, too much residue can be a problem. So, it interacts with, rideability in the field or also plugging up your planter. So that's kind of the trash aspect of it. But kind of, thinking about what's the actual, quality of residue or what's, good about residue. And that's the nutritional value of it. So in corn residue, there's a lot of nutrients tied up in it. So for nitrogen, for every 1 ton of residue that you have, there's 20 pounds of nitrogen within that 1 ton. And so, if we look at a 230 bushel an acre crop of residue that has around 5.5, or 330 bushel corn crop, it's around 5.5 tons of residue per acre, right? And in that, there's 108 pounds of nitrogen per acre. And phosphorus, and that's 21 pounds an acre. And then for potassium, that's 122. So that's treasure, right? It's all tied up. And the funny thing about treasure is, I think of pirates when I think about treasure. And if you're looking for treasure, you got to get the boat. And then you got to get the crew to go find it. And then once you find the treasure, there's usually a lock on it, right? So you gotta try to find a key to unlock the treasure within that. And residue is kind of that same way. And so how can we actually unlock the value of our residue? And I kind of like to think of it as a big system, right? Or a big machine. So I like to have the 3 C's. So there's gears. So the first one is convert. So convert, you're trying to do residue degradation. You're trying to take what's in the field and kind of accelerate that degradation. And then with that, after as you start degrading, what is it releasing? You're trying to capture it. So you're trying to capture the nutrient value that you're degrading from that residue, or that when you're degrading the residue. And then also we create from that, right? So everything, we've got the nutrients, we're trying to capture it, and we're trying to, increase yield with that, create yield and plant growth. So kind of, how can we do this as farmers or as researchers going into this? We kind of like to start, how can we improve it? So we talk about mechanical management. So starting at the combine right after harvest. So mechanical management, we like to think of, we have standard stock rollers or Comer BT choppers. So I like to think of this as like a steak. So do you like to eat steak whole, like with your bare hands, or do you want a knife and a fork to kind of cut it up, and does it make it more palatable? So it's the same way for the microbes, right? So do they like, the residue, more whole or, cut up into more pieces? So, if our residue has been mechanically sized, is that enough or do you need something else? So same thing with the steak. Do you want your steak seasoned? So, does the residue need to have some sort of fall fertility added to it as well to kind of encourage those microbes and accelerate degradation? So we kind of look at this with AMS, and you're like, okay, why AMS? Well, for 200 pounds an acre, you have 42 pounds of nitrogen and 48 pounds of sulfur. And why are nitrogen and sulfur kind of important for our residue degradation? Well, that's where our C to N ratios come into play. And so microbes really like C to N, or they prefer a C to N ratio of 24 to 1. And anything above that induces N immobilization. So that means that there's not enough nitrogen within those residues that the microbes can feed off of it to degrade it. They have to start pulling it from the soil. And that's where you start running into issues. Now, if you have those crops that have enough nitrogen in them, they induce N mineralization because the microbes have enough from that plant that they're releasing the excess back into the soil. And so, we're kind of dealing with corn stover. So, and also, if you're looking at, 250 bushel an acre corn crop, that's over 5.5 tons of residue. So that's a lot. So kind of, how can we look at this and, how can we take that, mechanical sizing and also the fertility aspect and how does this correlate actually into yield? And we've actually looked at this. So harvest method by AMS grain yields. So we have our two different harvest methods. So we had that standard residue, the non-chopped, and then we had chopped. And then we also did the fertility, so that fall application of AMS. And we looked at this over multiple years in different tillage systems. So in 2017 and 2018, we looked at conventional till. And you can kind of see in this, the addition of fertility did help in the standard as well as in the chopped for 2017, not so much in 2018. But then when we go looking into no-till, so like where we're really dealing with residue on the surface, a lot of residue, we see in 2020 and 2021 in both standard and chopped, the addition of AMS consistently improved yields. And so on average, regardless of the system, whether it's standard or chopped residue, with the addition of AMS, you're seeing a yield increase, especially in that no-till where we are dealing with more corn residue. So also in this, I like to go back to the common C to N ratios. I looked at AMS, which has nitrogen in it, but also has sulfur in it. So my kind of question is, could sulfur actually be at play in our residue degradation? And then I started thinking about, okay, well, we have these C to N ratios, but what is it? What are our C to S ratios that we're looking at? And actually, corn stalks can have a carbon to sulfur ratio of 350 to 1. And we really haven't looked into that yet, and that's kind of some of the work that I may talk about later that I'm getting into over the next couple years. So kind of some of our key takeaways from this. Adding fertility to the residue improves decomposition, no matter if it's, no matter if it's standard or chopped residue. So regardless of the mechanical management. And what does this kind of tell us? That those microbes really need nutrients too, right? So we need to be feeding them as well because they're not getting that from the residue. And so, residue and the C to N ratio, why do we have these C to N ratios? C to N is source dependent, so it depends on the crop that you're dealing with. And soil microbes like a C to N ratio, like I said, of 24 to 1. And why is this? Well, microbes have a C to N ratio of 8 to 1. So it's 16 carbon for energy, so they're trying to build carbohydrates, and then 8 for maintenance. And they also use that nitrogen within their cells for cell wall buildup or enzymes and proteins. And then also, C to N ratio, like I said, if it's greater than 24 to 1, it's inducing N immobilization. And then a C to N ratio less than 24 to 1 is inducing N mineralization. And so, how can we actually, with all of this, manage our residue effectively? So we've got those mechanical sizing of the residues, right? We looked at that avenue, and then we looked at fertility, so adding the nitrogen or the sulfur component. So we've chopped our steak, we've seasoned it, but also there's another aspect to it, and it's what I like to call the A1 or the steak sauce. So it's not everybody's using it. It's not always so popular, but it is a new avenue that we're taking, and that's actually biologicals, right? So that's a fall burnout application with bacterial blends. And there's this big, a big boom in the market of biologicals, and that's a lot of what I work with. And it's an interesting topic. And usually the biggest argument is what exactly are they, right? So in the crop physiology lab, we like to refer to, what are biologicals? We split them up into two groups, so beneficial microbes and then biostimulants. So beneficial microbes are really those living, your microbes, your living substances, and then biostimulants are the deads, right? So those are non-living substances. And when we've really focused on, the beneficial microbes, so the living. And so what exactly do those microbes do, right? Like I said, there's lots and lots of products out on the market. So in 2024, Dr. Sible actually did a survey over 155 products. And within those 155 products on label, 82% of them were for crop nutrition, 9% were for residue management, 5% were for plant growth, 3% were soil inoculants, and 1% were for drought tolerance. And I really want to focus in on this 9% for residue management. And I only think that's going to continue to grow as the years go on. And I think that's kind of the avenue that we're starting to look at, and how we can, kind of add on these biologicals with levels of fertility or other levels of management. And Dr. Sible, I'm going to hand it over to him, and he's going to go over how, we can kind of take multiple approaches and can they be synergistic.
Look at that. Seamless transition, maybe a few squeaky chairs. Well, thank you so much, Ava. So been doing a lot of background, really help set the stage. Why is residue important? The coolest thing is we've been talking about it, having conversations, as Ava pointed out, it's every farm, no matter how you farm, what crop, what system. The obvious that she mentioned, the cover crop, the double crop, but then the higher yield thing comes in, right? We're in Champaign today, Champaign County. There's not a lot of double crop, not a lot of cover crop, a lot of conventional high yield systems, still has a residue play to it. I love that steak analogy. The chopping it up, right? That makes sense. Start cutting it up first. Then we look at some of the seasoning. And just yesterday, she came up with the idea of, how do we think about the biologicals as the A1 steak sauce? Some people for their palate, some people for not. But it's the options we have. That's the importance of why we set up the stage today to talk about and think about agronomic management solutions for residue. And it's really the mechanical, the chemical, and the biological. How we then integrate that into useful systems that can have a benefit is where we'll transition now with a few case studies. I wish I had a perfect case study for every scenario, but we're going to focus today on continuous corn and cover crop systems with some of our latest data. But what we want you to do is also think about different key points, topics, concepts, and then how that might translate to your systems, your farms, if you're doing fall work or if you're not, and focus that on spring. So excited to show you what we have been working on, and we're going to do a little bit of a history on one of the earlier projects that I was involved with in the crop physiology program. And it came down to this question, right? Can multiple approaches to residue management be synergistic? And I want to be very clear, it's phrased this way specifically because it's not crop management, it's crop residue management. And that's the idea with that fall fertility. And the question why Ava talked about the microbes needing nutrients too. Sometimes I think about residues. Who are we managing? Are we managing the crop? Or are we managing the microbes in the soils to go after the residues, and then the crop comes beneficiary after that? So that's why we do phrase it. It's crop residue management, not necessarily crop management. And in a perfect world, right, can it be synergistic? Can stacking these different systems have a synergy plan, 1 + 1 = 3, so to speak? And we use our long-term continuous corn as a case study. Why do I like the long-term continuous corn case study? It's residue worst nightmare, worst case scenario. So why this is interesting, why it's such a worst case scenario is that, again, the crop physiology program led by Dr. Bilo, a couple of years ago, he had this really good idea to start a long-term site. And he started that site in 2003. And on this site, they were going to have continuous corn versus corn soy rotation, and then look at that year over year. And we are still managing those sites today, going into years 23 and 24 of continuous corn. So whenever you get to step into these legacy projects, it's always kind of a reflection moment. Where was I in 2003 when this site was started, right? So this is a picture of that site. You've got our continuous corn block here in the center, and then our rotated with beans on the right side, so that every other year we can go back and look at the continuous corn penalty when we go corn here and corn on corn here. So where was I when this was the first year they established this site? For those of you in Northern Illinois, you may know Edwards Orchard, Apple Orchard, and that's where I was back then in 2003. But I guess I always knew I wanted to be a corn agronomist. And lately, I think Soybean Association's happy. A soybean agronomist as well. So I need to maybe get a photo with a soybean carving there. But that's where I was in 2003. And then I got to work on this site about 17 years later in 2020 and 2021 when their two sister sites were in 17th or 19th year continuous corn. And we looked at those practices that Ava did so well, setting us up with the mechanical, the chemical, and the biological. First and foremost, long-term continuous corn, especially in a research field, not necessarily going to be recommended practice today, right? The long-term continuous corn unmanaged control plots had a 48, what we call continuous corn yield penalty. So CCYP is continuous corn yield penalty. That's the yield loss relative to annual rotation. And so this site, the annual rotation across those 2 years, corn after soybean was 201 bushels per acre. When we had then the 17th or 19th year continuous corn, it was 153. And to make it matters worse, I should note the 2 years here, Ava alluded to some of the results earlier, that was taken to no-till. Again, we set it up as worst case scenario to just get ourselves started on this residue management approach. So what did sizing of the residues do for us? Sizing of the residues got us 13 bushels back. So that is a reduction in the continuous corn yield penalty, 13 bushels less penalty, getting us back. Sizing across our data, in especially thinking continuous corn or corn residue management, tends to be the biggest return or the biggest response. That's the first logical step. It's just cutting it up, making it easier for the microbes to get there. Again, that is in our flat areas of Champaign. That might change a little bit for those of you that are in hillier regions thinking about retaining the residue as well. So considerations there, but that's typically been the best thing we can do if we had to pick one thing. When we added the ammonium sulfate on top of that, we only got one more bushel. And so to get combined, that's a 14 bushel reduction in the penalty. I can tell you, if you don't have chopping residue corn head, what happens if you had spread the ammonium sulfate on standard corn head stalk rollers? It was worth about 8 bushels. So 8 bushels if you just did the ammonium sulfate alone. And then where things got interesting is we started looking at these microbial products. We got another 11 bushels on top of that when we added the microbial blend. That shocked us. That's a really strong response to any management practice, let alone a biological. But if I had just sprayed the biological in the fall burn down, i.e. no sulfur and no sizing of residues, just standard stock rollers and then spray it, it was only worth 5 bushels. So it's this additive to synergistic effect. And when you sum that up, it was in total a 25 bushel reduction in the yield penalty, which in the case of any one thing by itself was only 13, 8, or 5. So you have to add them together to get there. And that's a 52% reduction in the penalty. But the key point is that any combination was better than any individual practice by itself. This is where we've started to then say, all right, that continuous corn, it gets us thinking. And then Dr. Allison Bryan before me did some studies on those same sites. We're seeing similar trends, the mechanical, then the chemical, then we might be ready for the biological, adding them in that order. But that's continuous corn long term. Not a very common system, right? I know up in northern Illinois, there's a little more continuous corn, but maybe not 17 or 19 years. So how do we apply these practices then to more modern systems, especially for our southern Illinois counterparts, right? Can we do something like that to manage our wheat straw when we're doing double crop? We've done some work there. Spray grade AMS at 4 to 5 pounds sulfur and nitrogen to the acre seems to be working for us. For those, considering that end, but I'm going to focus the remainder of the talk today on what we've been doing in cover crops. Here I have a photo of cereal rye, but we've also been rotating this with crimson clover because one of the challenges of cover crops, we know there can be a lot of benefits, but similar to continuous corn yield penalty, there is a, CCYP cover crop yield penalty. Can we manage the cover crop in the season that we're going to terminate it to maybe mitigate that penalty or turn it over a little faster? And this is then also starting off in a no-till scenario. So you can see we got no-till corn stalks, then that cereal rye, and I'm going to no-till beans into this. What have we set ourselves up for, right? We've got our vegetative rye cover crop, 26 to 1. So it's right on the cusp of where Ava set us up with that 24 to 1. But then our corn stalks, those are going to be 57 to 1. And while you might think nitrogen tie-up in grass systems is a common occurrence, is nitrogen immobilization in soybean systems something we really need to be worried about? Don't forget, soybean needs a fair amount of soil nitrogen to get it going, and the nodules can get a lot through the season, but the other half of soybean nitrogen can come from the soil supply. And if we immobilize the soil supply, that could potentially limit it. So the C/N ratio, it's not just for corn. On corn or wheat systems, we think about it's for all crops having this challenge of fighting the microbes for that nitrogen availability. So this is what we've been working on for the last 4 years. Well, three years, I guess. We got year four goes out this summer. And so this is a picture of that trial. It is small plot. So I do know I always like to show the types of studies and examples of what we're doing here. And you'll notice there's some treatment effects out here. We'll talk about that. And then we have some uncover crop check plots, but I have to give a big shout out to Illinois NREC. They have been funding this project for us the last 3 years, going into our fourth year. Looking at management approaches for cover crops. So what have we been doing? Well, it's going to sound a little bit like a broken record, right? So we are doing either standard stock rollers or we're chopping the residues, and that is in the fall with the corn harvest. So year one of this study was following corn residues, and that's just the visual of what that looks like. And there's two questions kind of behind this. When we're seeding a cover crop, do we need nitrogen availability for the cover crop to get started? How does sizing the corn stalks? Because I know it's typically a good practice for corn on corn, but does that impede the ability of the drill to get through and establish? There's questions there. And so that's the first question we wanted to look at. And then adding other factors in, there's secondary questions. So how does harvest method affect cover crop establishment? But then when we follow this with biological or sulfur treatments, does that enhance the rate of biomass degradation and our nutrient release from those cover crops? So it's a two-step process. First step, got to make the residue of the cover crop establish biomass. Second step, get it to break down when we get into the cash crop. So that's the approach and the style, the thought process behind this study here. So we then follow that with our cover crops. So ahead of soybean, in the fall, we're going with cereal rye. But then when we go to our crop rotation to corn, we're actually putting crimson clover in. We've tried the last 2 years to integrate that with the tillage radish. Hard to get that established in the fall here. So the tillage radish didn't make it, but the clover did. It was one of the photos on the title slide. Looked very, very nice out there. But it's a long-term static approach because the treatments that we're talking about, there's questions about what if you do these year over year into the same system? Because a lot of times in research, we sometimes get stuck doing 1 year in field A and then next year repeating that in field B and then in field C and get 3 first-year looks. We're looking at the long-term approach with this study. So it's kind of like, Dr. Bilo had his long-term continuous corn site. We'll see how long I keep this one going, but it's like my long-term cover crop site that we started here a couple years ago. Then we're asking ourselves, what can we add to the termination pass, right? So we are going after that sulfur. Just because we know nitrogen can be a good, useful tool for residue due to C/N ratio, but that 350-to-1 sulfur carbon rate or carbon to sulfur ratio just kind of makes me question, are the microbes becoming sulfur limited when it comes to residue breakdown and degradation? Because maybe we have nitrogen out there, especially in a dry year. Maybe there's some retaining from that corn crop, but are we sulfur? So this is why we jump straight to ammonium thiosulfate. We are adding that to the sprayer pass. The idea is a one-pass system, or can you granular spread AMS? That does require a second pass, so you have to think economics on multiple passes. We're going to focus more on the liquid forms today. For those curious, we are running 20 pounds of sulfur per acre, so that's going to be an 83-pound AMS rate or a 7-gallon ATS rate, which that is a hot rate. We're doing some new studies, I think, moving forward. We're going to look closer in that 3 to 5 gallon range. Some feedback there, 7 gallons. While it gets 20 pounds of sulfur, maybe we don't need as much, but that's why we're looking at sulfur. Not just that C/N, but that C/S ratio. I want you to think about that for high residue systems. And then we get into the A1 steak sauces, right? The biologicals. What happens if we add a living blend or a carbon blend? Compare that in his full factorial design. Why did we pick a living versus a carbon blend? So the living blend has these microbes as the active ingredients. We didn't, in the interest of time today, show you the other things we did with that biological survey. But of those 155 products, I looked at what were the active ingredients listed on labels. So not just what products are out there, but what microbes are the companies formulating in those products. And so 5 of my top 10 microbes are in this product. So their bacillus are very representative and that trichoderma of the biological market. Of those 155 products, these were 5 of my top 10 most common active ingredients. That's one of the reasons we went with the living. And then we have our non-living, which is just sugar, think of like candy, and then humic acid, which is maybe it's a housing system for microbes, maybe it's chelating nutrients, maybe it does break down and creates a carbon source down the road. Maybe, it's our simple sugars, our candy versus our complex carbs that we think about. Why do we have these two strategies? What is the point and intent of comparing a living and a non-living? Well, when I talk to someone, they say, Connor, why would I pay for a microbe in a jug when I got billions of them already in my field? It's a great question, right? So here's the concept behind applying a living microbial product to residues, especially in these cover crop no-till systems. Where is the residue? On the soil surface. How does residue break down? Via soil microbes. Unless we get incorporation of the residues into the soil, the workers and the microbes in soil can't get to the job site very quickly. You need good splashing rains, get some soil on the residues. It just takes time. Now, it will happen, but it's a slow process to start. And especially as you move north, that natural window of decomposition gets shorter the further north we go. And so the idea of putting a living microbe on the residues in fall case from what we did earlier, or now in the spring at termination, is it's putting the microbes that do the breakdown on the residues right from day one that we want to start breaking down. That's the concept, the theory behind it. The alternative is I've got billions of microbes in my soils, so I just need to wake them up. So what if we put sugar and humic acid out? That sugar, it's probably gone within 48 hours, would be my guess. But it's like setting the alarm clock off for your native microbes. Their feet have hit the floor, and they're like, well, I'm awake. I better go to work or go make the coffee. They keep then going after what's the next food source. Hopefully, it's your residues. So just some thoughts behind strategies to residue management. Should we apply living microbes or should we just apply some sort of carbon source? So that's why we selected the products that we did in this case. So again, just a reminder, this is a no-till 4-year study to start. We're going in year 4. I think we're going to keep it rolling after this. Static plot. And why I think this is so interesting is because year over year, we're putting those same treatments to the same plots. That means some plots are getting 20 pounds of sulfur every single year. Other plots are getting the same microbes every single year. And do the effects change over time when we do that? Moving forward, we're interested, the sizing component hasn't had much difference, which is a good thing on the idea from the yield side. And so we might be able to look at what if you continue doing certain managements and then pause on some and how long does it residual last. But here's what that 2-year cycle looks like, or at least the first 2 years. So you can see fall of 22, we had cereal rye. Spring, then we followed that with soybean. Fall of 23, we put our clover radish mix in, got the clover to establish, and then we followed that with spring 2024 corn. And then you could repaste this. So fall of 24, we put cereal rye. Spring of 25, we had beans. This last fall, we put in crimson clover. And this spring, we will plant corn for the 4th year. Just a little bit of looking at the residue value and some of the thoughts behind why we want to potentially manage our cover crop. So for those that are interested, this is the specifics of how we got that trial going. Again, we got the cover crop in October 21st in that first fall. We terminated late April. All of our cases, we've waited about 3 weeks between termination and planting. So it's not plant and green, it's terminate, then plant. Planting date then May 15th for the beans, and then a little bit of the specifics on the genetics that we used, and pretty good soils to start with. Not going to lie about that. Good organic matter to start, good PK, set ourselves up for good yields moving forward. But what's that cover crop get us in that regard? But what is that nutritional value of cereal rye? Because Ava talked about nutritional value of corn stalks, but what about the cereal rye? So this assumes 2 tons of residue per acre, which we did actually achieve. We were right on average. I think it was 2.1 or so tons of residue. That's a little bit on the high end. So for those that follow different cover crops, I think the minimum for nitrogen retention to maximize nitrogen retention and minimize yields is 0.5 to 1 ton, right? If we're above 1 ton, we really start hindering the potential of yield. However, for those that talk to the weed scientists, 2 tons or more is the best win scenario for weed suppression. So we're perfectly where we want to be on 2 tons, being just on the cusp of probably too much, but maybe right for weed suppression. How do we manage it? But what do you find nutritionally in 2 tons of cereal rye residues? Well, per ton, that's 37 pounds of nitrogen. And so per acre, we get about 88 pounds of nitrogen, 33-pound equivalent P2O5, and then 153-pound equivalent of K2O. This was sampled at vegetative stage, so we hadn't quite gone into booting yet, and we didn't let it head out. These numbers will vary a little bit year to year based on the conditions. So if you've seen other reported values, they'll be flux. But the key point here is there's a lot of nutrition in that cereal rye. And this is at termination, which is in the spring. So we're trying to get it to break down springtime through that season for that soybean crop. And I'm the optimistic guy. I want 80 bushel soybean. And so you can see if I want 80 bushel soybeans, I need about 330 pounds of nitrogen, 60 pounds of P2O5, 230 pounds of K2O. In that cover crop are these values here. In theory, if I were to release 100% of those nutrients in that season, got about 30% of my soybean nitrogen needs, 60% of its P needs, and 70% of its K needs. That's pretty cool. That's the idea. And why this is important to think about breaking it down is we terminate in that April to May window, and the beans are finishing up their yields end of August, September. It's a very short window to try and get these things to break down, trying to enhance the natural rate of decomposition. We'll talk a little bit later about, if that's stealing from the future crop. This is the potential. Here's the interesting thing, though. If I even get half of these nutrients to release, that's still about 15% of my N, 30% of my P, and 35% of my K. So it's the treasure value that Ava was talking about earlier. So the key then is you have to get that to break down. So how did our treatments then influence that breakdown? What we did is we sampled 2 bags at termination, but we left them in the field. The first one we picked up at soybean growth stage R3. So early July, we picked up the first bag. Then at R7, at this point, yield's been decided. How much did we get out in that season? We picked up the second bag. And we're looking at the main effect of the sulfur. And what you'll notice is, by and large, it's not huge difference. We had about 57 on average percent of that residue had degraded by R3, and almost 86.5 if we average that of that had broken down by R7. Now, one of the things that kind of was curious to us, we didn't expect this, right? We just set up the whole last 35 minutes, I'm watching my clock here, telling you why sulfur helps residue break down. And then I just put data on the screen that says, in this case, it kind of actually reduced that rate, right? So the ATS values are less decomposition. So Connor, what's going on here? Well, one of the big differences between the work that Ava talked about and what I talked about with continuous corn, those residues are already dead, right? They're already broken down. They're already at a high C to N ratio. That's making then the microbes need that sulfur a little more. This is what our residues look like when we're spraying at termination. That ATS burned that crop real fast. You can see that right here. The nice thing is when the grad students spray the plots, we know exactly if they put them in the right spots or not. This was within 36 hours of spraying. You could see it to the row. Whereas without ATS, it's starting to die back a little bit, but it's definitely not as injured. If I give you an apple that's bruised or an apple that's intact, which one do you want to take a bite out of? Probably not the bruised apple. It's the same concept with microbes, right? They would rather break down the good green nutrition stuff because the ATS is maybe not as palatable in this situation when you're treating green residues. We'll talk about yield differences in a second. So that's just focused on the residue degradation and why green tissues may not be breaking down as fast. The good news is it was pretty close. So keep that in mind. It's pretty close. What about, though, the biologicals? Did they have any effect on that residue breakdown? And so the same 2 growth stages versus our living microbial and our carbon, and in the right direction, right? So that carbon blend gave us about a 4% advantage on that decomposition. The microbial blend only 1%, so those are statistically the same. But the carbon blend, all right, waking up the native microbes seems to be a good trend. And that then carried through, not as strong of an effect, but it did retain through the end. So that's what we kind of see with these residue managements for cover crops spraying green. The ATS burns the residue, and it does reduce the total decomposition. The biologicals did have some effect, especially the carbon blend, on increasing it. Just thinking about the palatability of the microbes. One cautionary note, ATS, if you burn the residues that fast and you have a herbicide that requires translocation, One year we did have to re-terminate the crop because the ATS didn't let the herbicide translocate. So just a cautionary note, you might want to separate your herbicide pass from your ATS application if you're going that route. So what about the crimson clover? So we do this in a year, and we'll get to yields here in a little bit, but we're interested in this biomass, this treasure, right? So very similar timeline. We got the cover crop in 10 days earlier than the first year. We had a wetter spring, so we couldn't terminate till May 1st, and then the rains came back. So we did get planted a little late, but we had a 111-day corn hybrid, pretty good density there, and then we were able to get to that right on Halloween. What did our cover crop look like? Looked like this. It's great, beautiful, looked good to go out there. So it had flowered at termination for those curious. But when we terminated, what was the nutritional value? And we happened to get another 2 tons. It was about perfect. In that clover, we had 92 pounds of nitrogen, 24 pounds of P2O5, and then 132 pounds of K2O. A lot of potassium in those residues. And knowing that it's a no-till cover crop system, I put my yield threshold for corn at 230 bushels in this case. And a 230 bushel corn crop needs about 260 pounds of N, 100 pounds of P, 180 pounds of K. If I were to release 100% of the nutrients from that cover crop, I would have gotten about 36% of my nitrogen, 25% of my phosphorus, and 70% of my potassium. Again, we're not going to release all that nutrients that fast. And even as they release, who gets it first? The microbes or the plants? But if I could even get half of that to release in that short season window, that would be a positive benefit. And that is what we are going to be seeing in the yields when we follow it through. Decomposition trends of the treatments were similar in the crimson clover as to what we observed with the cereal rye on that end. So now we need to get into, we set the stage, what we've done, but you all want to see the yield values, right? So first and foremost, our untreated, uncover crops control, really good yields. I can't complain with these. 87 bushel beans in the first year, 76 last year, and 260 bushel corn in the middle. What did the cover crop do without management? A couple things going on, right? We lost yield in both scenarios. We had a 6 bushel penalty on the beans the first year and an 8 bushel penalty on corn the second year. Again, 2 tons of cover crop is a heavy biomass, great for the weed control, not so great from yield perspective, and more than enough to capture a lot of the nitrogen if you're using it for that reason. What really gets me excited and why I'm really excited about what 2026 is going to bring, look at this 1 bushel difference. Has the system finally adapted to the cover crop? And in 2026, am I going to see the unmanaged cover crop go positive, right? We often hear folks say, I tried cover crops, didn't work, I'm moving on. Sometimes it just takes time for that system to develop and adapt. Is that what we're observing here? We'll let you know in 2026. However, all these managements on the left side of the screen, if I can mitigate this penalty sooner, that's the goal, right? Can we minimize this more quickly than waiting for time to do it? Here's what we see with yield differences if you're to do one thing, just the microbe, just the carbon, or just the ATS. If I had to pick one thing, it's fertility, right? It goes back to the theme of the day, mechanical, then chemical, then maybe biological. And even then, it wasn't a huge response, right? We got a significant bump on the beans the first year and modest bumps here in the next 2 years. But where we see the cool and exciting thing is when we add them together, in the first year, you'll notice it was ATS driven. But in the next 2 years, we are seeing an additive system approach on the bean side, right? So if I add the 2 and the 1, I get the 3. If I add the +2 and -1, it's actually +4. But the corn, that is synergy, right? So if I take 3 bushels to the ATS with 0 on the microbial, but I get 7, or 2 + 3 getting 10, synergy. This is just an anecdotal comment about the biological market, what Ava's data is showing, what our data has been showing. They tend to have stronger responses in grass crops. In corn, our data is much more consistent than in beans. Corn's making yield decisions at key growth stages, and if you can influence the crop, early vegetative pollination, maybe you get the yield return. Soybeans, gosh, we love them when they throw 87 bushels at you, but they are making yield decisions every day, R2 through R5, R6. So it's just really hard to get that moving target consistently. But the theme that we see with cover crops, that we saw with continuous corn, that we've also anecdotally seen in our double crop, we have a few studies there, is this systems approach. It's not necessarily the one thing you do, it's then adding them together. And what you'll notice in that corn year, we actually outdid the penalty, 264, is better than the uncover crops control of 262. And in the beans, the last three treatments where we had the ATS have all also outcompeted on that unmanaged control. So that's also sulfur response. Again, in year 3, we've put sulfur out 3 different times in a row, but it's helping overcome the penalty earlier than we would if we just waited across the top. So that's what we're seeing in cover crops. So with that, we can manage them at termination to enhance breakdown and minimize penalty. The nitrogen sulfur source is the best single management recommendation. Do watch your herbicides if you're using a liquid source. Biologicals do have some benefit, but we really see that they're working together with the fertility rather than just trying to use a biological on itself. The other things to note about residue degradation studies: if you enhance the residue decomposition and therefore enhance the release of nutrients from those residues, you have accelerated the natural process. A lot of people say, won't those nutrients release eventually for the next year's crop or even 2 years crops down the road? Completely, right? We are enhancing the cycle in the system. You have to remember that. That does give, in our cases, higher yields, but higher yields also means we have higher grain nutrient removals, and why we can't overlook the value of nutrient management and fertility is that we have to ensure the long-term sustainability. If we really start to go after residue and rely on the residues and the soil nutrients over time, there might be a point where we have to put that back. So just a reminder, residue is trash. We love the nutrient, or not trash, is not trash. We love the treasure value of residues, but treasure, it takes time, investments to build that up and make sure we don't just drain the bank right away. So keep that in mind as we go through there. But in the last few minutes, this might help us get into the discussion. I'm going to hand it back to Ava. She's going to walk you through what are we doing next, because there's a few questions we have not yet answered.
Hi, Ian. All right, so I'm kind of switching over from my master's and my PhD. So kind of what are those future avenues are we looking at for residue management, right? And those kind of come from key grower questions. Some of those can be, is residue management better for soybean, or if you're going into second year corn, so like continuous corn? And also, should your residue digesters be tilled in after application, or are they working better in a no-till system? And then also, my biggest question is, does a little bit of nitrogen or sulfur help increase activity of applied biologicals? And we've applied AMS, we've looked at that, but could there be some other play? Is it just the nitrogen? Is it the sulfur and the nitrogen together? So I kind of look at that component. And also, does the timing of application increase biological activity? So if you're applying in the fall, do those microbes actually overwinter and work up until planting in the spring? Are they working fast enough? And then also, if you're applying those biologicals in the spring, do they actually have enough time to work before planting rolls around, or are you getting the benefit out of them? And also, does reapplying year after year have a compound effect? So if you're applying, biologicals or fertility year after year, is it going to have a compounding effect on that residue degradation? So kind of some trials we're putting in. So the great thing is about my PhD, I kind of started it recently, so this past fall. So I started before I even graduated my master's. So kind of in fall 2025, we have corn stalks. So any of the treatments I'm going to be talking about, they were applied this fall to corn stalks. So in summer 2026, this upcoming season, we have second year corn or first year soybean in our trials will be in strips. And then summer 2027, we'll have a third year corn, continuous corn, and then we'll have a first year corn, so soy into corn. And then summer of 2028, we'll have a fourth year of continuous corn or a first year into soybean from that corn into soybean rotation from 27 to 28. And we actually have two different kind of setups that we're looking at. So in this, like I said, we have the 2 crop rotations. We also have 2 tillages, so no till and conventional tillage. I have a nitrogen component in this one with UAN, also with the biological component. Then it also has that application timing. So is it working better in the fall or the spring, or should you be applying in both? And then also we looked at once again the 2 crop rotations, the 2 tillages, and then also looking at ATS and UAN. So is it more of a nitrogen play or is it a sulfur play? And then also, if you add the biological with that, is it improving it any? And also a big question is, how do you actually measure residue decomposition? I know we've been talking about how we've got so much of it in the field that it has all this nutritional value, but how do you actually measure that, in small trial research or just in general? So it's actually a grad student's favorite job from what I've learned. It's residue sampling. So we actually go out into the field, we do small plot research. So we go out into our small plot and we take this little square, and within that square, we take out all the residue and we put it in mesh bags. And those mesh bags, one goes back with us and the rest go back into the field. So we're kind of trying to this is the best way we can kind of simulate natural decomp conditions in the field by putting it in these mesh bags so it's exposed to the elements. And so then throughout the season, we kind of take those bags in. And so this year we did 5 different timings. So one of those bags comes back with us from the plot, and then 5 more get left out. And throughout the season, we kind of pick those up. And why do we do that? Well, we kind of get to build what I call decomposition curves. So this is not any of the data that we have yet. We don't have any as of yet. But hopefully from this, I can kind of build a decomposition curve so we can see, when in the season are we seeing, the most decomposition, and also what's the nutrient value that's coming from that. So the results for those will be coming in fall of 2026. So I'm super excited to be able to share those with you hopefully in the future. But with that, a special thank you to Illinois Soybean Association and Field Advisor for giving us the opportunity to speak on our research.
And with that, we'll take questions.
Great. Thank you both. That was very informative. We did have one question come in through the Q&A. I'll go ahead and verbally mention it. The question asks, I thought potassium released rather quickly from residues on its own, up to 70% returned post-harvest. Do you have anything to comment on that?
I would say correct. So yeah, potassium does not actually assimilate into plant matter, so it's in a solute form and it can leak out. So yes, potassium, I would expect a lot of that to be available. The nitrogen, the phosphorus, we got to break it down. But great comment, and glad we got that off the bat first too. Yep.
I have one question that came from the submissions, and you've touched on it a lot throughout your presentation, but just kind of to round things up a little bit, especially in today's tight farm economy, they're asking, does residue management make economic sense? So that is a big, broad question, but I think just allude to that and just kind of maybe hit it home of why it does or why it doesn't.
You want to give it a shot? You want me to take it? All right. So economics is important. We have to always ask ourselves that. I would think on the mechanical side, that's a huge upfront cost. So the mechanical approach, no matter how you're doing, there's a lot of different ways to get sizing heads, or if you're doing aftermarket things, there's a lot of options out there, but it is an equipment purchase. And that will have to then, you have to remember and remind yourself, it's probably going to take a couple years for that to pay itself fully back. So that's one big thing on the equipment side. The good news is it is a one-time, for the most part, investment, and then there's some maintenance after that. Eventually you may replace, but one big upfront cost that then returns over many years. The individual products fluctuate back and forth, and a lot of it on the biological side, 3 or 4 bushels pays back for the product. But how consistent can we expect that? That's partly why we're looking at these systems where we may get better consistent return. The AMS ATS, and again, I know the values change, and that 7-gallon rate, I know I've talked to folks, is a little bit higher, maybe economically, but I've heard feedback 3 to 5 gallons maybe have the economic return in the right year. That's why Ava's project she put up there, we're at 3.5 in our new studies moving forward. So you definitely just have to keep that in mind. But back to your basic question, does residue management make economic sense? I think it does in the long term, especially if we're in more conservation-based systems. The one thing we didn't talk about today, and I might get chased out of the room for saying it, what's the best thing to do for residue management? Tillage. Right? I mean, hands down, that's the best thing. So if you're in heavy tillage systems, maybe we don't need additional practices. That's partly why Ava's also got her brand new project looking at tilled versus not tilled. I do think that if you're more no-till or these cover crops, you're going to probably likely to see a better return on those investments.
I thought you were going to say it depends, which it kind of does, but
I'll save that for the next one.
Yeah. Well, we didn't have any more questions come in. You guys provided very thorough information today, so I suspect people are going to sit on it, probably think it through, and I'm sure their contact information, if you just Google Illinois Crop Physiology Lab, you can find their contact information there and follow up. And like I said earlier, we'll get the live recording. So if you want to rewatch it and then think of more questions, they'll be happy to answer those. So anything else, anything you forgot, any other points you want to hit home before we leave today?
Keep the questions coming would be the one thing. So Ava's projects came from grower questions, the fall versus spring, the do I till it in or not. Your questions help us make sure that we have the right projects in place. So I'd appreciate, don't hesitate to follow up if you didn't want to put a question live on air. Be safe today for those in the storm zone. We'll throw that out there too. See how this afternoon and evening goes on that end. But I think residue, whether you're dealing with it now or in 10 years, it is certainly going to be something to consider. That would be, I think, the big takeaway. It's every type of system. Harvest index is the percentage of grain versus total biomass. And over time, we've increased that a little bit, but that's over decades. And breeding, what this means is in today's, next 5 years, that bushel value that Ava showed, every bushel of corn giving you 44 pounds of dry matter, that won't change. So as you go up 10 bushels and then 20 bushels, that residue is certainly going to be something that continues to build. And if we haven't been thinking about it, we think it's a time to be considering it. I know Sean Castile has been looking at harvest spread behind the combine, right? We didn't talk much about that. That's where it starts. When you harvest this upcoming crop, I know we're trying to get it in the ground first, being spring, but how you spread the pattern, more consistency is definitely where it starts too. So just always be thinking about it every time you're doing something on the field.
Mm-hmm. Ava, anything else you'd like to add?
I don't think so.
Does it scare you when you put the timeline up there and realize you won't be done till 2029?
We just got a quick question in. I don't know how long it's going to take you to answer it, but someone asked, what about short corn versus tall corn? Are you looking into that?
So I would like to look into that. We won't be able to do it this year, but I'm hoping to maybe look for that in the coming years. That's kind of on the drawing board still yet. So
yeah, so the idea is with that slightly more thicker stalk, does that stalk material degrade differently on short versus tall? For those curious why that question might come in. Valid question. One we don't know yet, and as Ava said, it takes a setup year to get the residues, but it's one we've considered as well. I know leaf biomass necessarily is pretty consistent, short versus tall, so it's mostly focused on how well do the stalks degrade. Great question. One, here we go. Kelsey is saving it. It depends, but we'll find out.
Yeah. That is a good question to ask. All right.
See?
Well,
Research project.
Yeah. Well, we're coming up on our time today. I want to thank Connor and Ava again. Thank you. Like I said, it was a lot of good information to sit and think on, especially as we approach planting season and the tractors rolling through the field with the presenter. So thank you both again. Thank you to everyone who attended today. The recording will be available hopefully this afternoon, if not tomorrow, on Field Advisors YouTube channel, and then we'll email it out to everyone that registered as well. If you're a CCA, please scan the credit right now. If you're watching the recording, we recommend self-reporting. And if you need assistance, you can email us at fieldadvisor@illusoy.org. Our next webinar to be announced, but we will certainly share that information once it's available. So thank you all again for tuning in, and we'll catch you next time. Thanks all.